So just like that last question on your quiz, we are looking to start to find all of the zeros or all the x-intercepts of these polynomial functions. But they're going to get more and more complicated, so we're going to have to add more and more tools into our toolbox to be able to find these zeros. The first tool in our toolbox today is called the rational zero theorem, or the rational root theorem. Basically, it says that if you have a polynomial, you have these integer coefficients p over q in lowest terms, that is a rational zero of f. Then p is a factor of the constant term and q is a factor of the leading coefficient. All of that to say, you are going to make a ratio p, which comes from the constant term. Any of the numbers that would multiply to a sub 0 are p values. And q, which is a factor of the leading coefficient, this number right here. So the two things we care about for the rational zero theorem is the leading coefficient and the constant. What we're going to do is we're going to make the ratio of all of the factors of these different terms. Okay, this makes a lot of no sense until we see an example, and then you're going to see where I'm talking about these different things coming from. So again, the potential rational zeros that we have for all of this come from the factors of the constant term divided by the factors of the leading coefficient. So we're going to do combinations of numbers. In this first example, we're going to just list all of the possible rational zeros for this function, which means we need to know the constant and we need to know the leading coefficient. So the constant here is 4. What are the numbers that multiply to 4? I'm going to change where I'm writing this. Okay, again, what are the numbers that multiply to 4? 2 and 2 totally works. What else? And then 4 times 1. Every single one of those numbers, 2, 1, and 4, we're going to use as a value for p. Okay, what are... I don't know what words I was just trying to say out loud. My q value is -1. What are the numbers that multiply to -1? -1 times 1, yeah. And I'm actually going to drop the sign on purpose. Okay, we don't really need to worry about the sign. I can't like talk and write at the same time today. We're not going to worry necessarily about the sign of p and q because we will use both the positive and negative version of them anyways. Okay, so my list of potential rational zeros is what I'm going to call it, or possible rational zeros. This is Miss Quigley notation for potential rational zeros because that's way too many words. Is the combination of all of the numbers on top that are pink and all the numbers on bottom that are blue. What's up?
So you got the 4 constant.
Yes. Okay, so what we are going to do is we're going to make these ratios. The first one I'm going to do is positive and negative p's over q's. So if I start from, I like to go from smallest to largest. So the smallest number on my p list is 1 over 1. My next smallest number is 2, going to be over 1. My next smallest number on my p list is 4, and it's all going to be over 1. So I'm making a list of all of the p's, 1, 2, and 4. I don't have to do 2 twice because it's a list, so it's already on there. Divided by any of the factors of q, and I don't have to do 1 twice because it's the same number. Which means that my potential rational zeros, when we reduce all of this, is plus and minus 1, plus and minus 2, and plus and minus 4. Those are all of the potential rational zeros that I would have to try if I was trying to find all of the zeros of that polynomial. Let's do another example before we ask questions because I think having 2 might bring up some better points for us or maybe better questions. So again, I'm going to use the rational zero theorem, rational root theorem, to list all of the potential or possible rational zeros. I need the constant and I need the leading coefficient. Let's factor those two numbers. What are all of the numbers that multiply to make -2, but I don't care about the sign? 2 and 1. Is there anything else? No, we're good. All right, let's do the same for Q. What is my leading coefficient? 15. And let's write this list in an organized fashion. What's the smallest number that can, like, pair? 1 times 15. What else? 3 times 5. I like to do this in a number order so that I make sure I get all of them. Okay, we need to make the combinations of all of these numbers for our list of possible rational zeros. Possible rational zeros. This list is plus or minus 1 over 1. Then I'm going to have plus or minus 2 over 1. Do we follow? To keep this in an organized fashion, I'm going to change to the next smallest denominator. So I have to repeat my numerators of 1, this time over 3, and then 2 over, it's the wrong color, 2 over 3. What's the next smallest denominator I need to use? 5. So this time these are going to be over 5. So it's going to be 1 over 5 and plus or minus 2 over 5. We got one more denominator to use, which means I'd have plus or minus 1 over 15 and plus or minus 2 over 15. So it's a combination of all of the possible factors of P divided by all of the possible factors of Q. Do we see that? Which is a lot, I know that. So when we write this down, we're going to simplify as much as possible, which means that this would actually be plus or minus 1, plus or minus 2, plus or minus 1/3, plus or minus 2/3, plus or minus 1/5, plus or minus 2/5, plus or minus 1/15, and plus or minus 2/15. Now, on your homework, those may be in number order and separated by plus or minuses. It kind of is varying based on the question you get. But I'm okay them being written in this logical order as long as they're all there. Okay, now that we've seen 2, what are your questions? Because I'm sure we have some. But now we're going to apply this potential rational zeros list to an actual problem. So the goal of today is to find all of the zeros for polynomial functions. And a lot of these are going to be ones that don't factor cute. So we have to have other things that we're trying. So when we're finding the zeros for a polynomial function, we will need to list all of those possible rational zeros. Then use synthetic division to test the possible rational zeros and find an actual zero. Then use the quotient from the law of synthetic division to find the remaining zeros of the polynomial function. So let's first just attack number 1 and let's find all of the possible rational zeros. Okay, if we're doing that for this problem, what is Q? -6. What is, or sorry, I think that was P. That's P. Which one's Q? 1. So our list for P, which is -6, I ignore the negative and I'm going to make this list make sense. It's 1 times 6 and 2 times 3. For Q, that's a 1, which means its list of numbers is 1 times 1. So my list for potential rational zeros would be plus or minus 1 over 1, plus or minus 6 over 1, plus or minus 2 over 1, plus or minus 3 over 1. Bless you. Does that make sense? I didn't color code that one, but are we okay? Now, all of those numbers are nice and neat because they're divided by 1. So just for my visual, myself, I like to just see them as actual numbers, not as the fractions, just to clean up my brain. Optional step there, as long as you recognize those are the same numbers. So I need to look at this list of 8 numbers and figure out which of them actually have actually are zeros of the polynomial function. So we go back to what we did last time, and we actually use synthetic division to test. Now I'm going to test them in a normal order, which means I'm starting at the beginning. I'm going to test the number 1 with synthetic division. Synthetic division would list the coefficients out. So this is 1 and 2 and -5 and -6. My pen just kind of malfunctioned. What were the steps for synthetic division again? Bring down, multiply, add, multiply, add, multiply, add. Since this has a remainder, is that a factor or is that a 0 of this polynomial? No. So 1 is off the list. Let's try -1. If we synthetically divide with -1, we'd have 1, 2, -5, -6. We bring down, we multiply, we add, we multiply, we add, we multiply, we add. Since the remainder is 0, is -1 a 0 of the polynomial? Yes, this is what we want. We want the remainder to be 0 because now I know that out of my list of potential rational zeros is the one that works. So we write the quotient from last class. This is the quotient. Oh, highlighted in the correct color. This is the quotient. This would be your divisor. So this actually would factor or would divide out to be x plus 1 multiplied by x squared plus x minus 6. If I keep going now, we look at that purple quotient to see if we can solve it. If it's easy to factor, then you're good to go. If it's not easy to factor, we will have to take another additional step to do this. Can you factor that purple thing? What multiplies to -6 and adds to +1? +3 and -2, which means that my zeros to solve this function, to find all the zeros, would be at x equal to -1, x equal to -3, and x equal to 2. So this is essentially like what we did at the end of last class, where I gave you a 0, you synthetically divided it, and then factored. It's just that now I'm not giving you the hint at the beginning of what the 0 is. You use the list of potential rational zeros to figure that out.
So we just like, even if it kept going, we got all the way to -3.
Sorry, I had to register to vote. You're good. I'm glad you registered. Yeah, no, if 1 and -1 didn't work, then you would try 6, then -6, 2, then -2, 3, or -3. One of those has to work. Could be more than one. And in fact, don't write this down, but I want you to watch. Okay, if after I did this synthetic division right here, this guy, I tried an additional potential rational zero, like 2, I'm fast forwarding to 2. If I just tried +2, I would be dividing it by 1, 1, and -6. That's my quotient. Bring down, multiply, add, multiply, add. Oh, snap. 2 is also a factor. And that makes sense because, look, we have 2 on our list. So it can work this way where we synthetically divide instead of factoring, because those potential rational zeros are going to be on your list.
Oh, so once we get our answer, we're also
Yeah. So once we at least have one factored out, we can continue to synthetically divide this quotient if we wanted to. But if it can factor quickly like this, if we know it's a quadratic, like let's just do it factoring wise because it's pretty quick at this point. Yeah? I'm going to erase this so nobody's like, what is that? Oh, erased everything. Okay, can we see another example like this? Sure, okay, great, thank you so much. We're gonna find all the zeros for this polynomial function, but I want you to take over first. I want you to find the list of potential rational zeros for me. I'll tune back in when it's time to test them, but just write that list for me with the P's and the Q's. For the p-value, the p is -3, or the number we're getting the p-values from is -3. But of course, I don't care about the sign. The numbers that multiply to 3 are 1 times 3. Our q is +1, which is 1 times 1. Amazing. Okay, so your list of potential rational zeros would be the combination of those factors. Our potential rational zeros are ±1/1 and ±3/1, which again, I like to see them as regular numbers if possible. So ±1 and ±3 out of fraction form. My brain just sees them better that way. That means we have 4 numbers to test. Let's do this in an organized fashion. We want to see which of them actually divides evenly so that it's a factor of this polynomial, or it's a 0 of this polynomial. Let's start with 1. Our coefficients are 1, 7, 11, and -3. We bring down, we multiply, we add, we multiply, we add, we multiply, we add. Is this a factor? No. We need that to be 0. So sad face. Not what we wanted. So we try the next one. +1 is off my list. I try -1. Bring down, multiply, add, multiply, add, multiply, add. Is -1 a 0? No, sad face. We try some others. Let's try +3. Coefficients 1, 7, 11, and -3. We bring down, we multiply, we add, we multiply, we add, we multiply. Was that 129? We add 126. Is that one a factor, or is that a 0? No, we better hope this last one works. I'm gonna drop down because I ran out of space. This would be -3. Ooh, I hope this one works. 1, 7, 11, and -3. We bring down, we multiply, we add, we multiply. That's negative. We add, we multiply, we add. Oh, thank goodness. The last one finally worked. That's what we want. Which means that I have a quotient of x squared plus 4x minus 1 and a dividend of x plus 3. So I can go ahead and write that as x plus 3 and my quotient of x squared plus 4x minus 1. Now if we start to do this one like we did the last one, we try to factor the purple thing. Does it factor? Are there any numbers that multiply to 1 and add to 4? Nope, unfortunately, it does not factor cleanly. So we go to our variety bag of ways to solve a quadratic, because that purple thing is a quadratic. What's the foolproof method for us to solve? Let's do the quadratic formula. It works every time. We were out of numbers on our list of potential rational zeros to divide by, so I couldn't do another synthetic division. There was nothing left. So we have to go ahead and use that quadratic formula. Does anyone remember it? So -b plus or minus the square root of, keep going. Very good, all over 2a. Now I think before, since in the first part of this chapter, we were looking just to plot x-intercepts, so I told you to just chunk that into a calculator and go. But this one, since I want solutions, I want exact answers. So we are going to have to do this one by hand. But if we start condensing with that discriminant, 4 squared is 16. 4 times 1 times negative 1 is negative 4, but we're subtracting it, so that's going to be 16 plus 4 over 2. What is 16 plus 4? 20. So this is negative 4 plus or minus the square root of 20 over 2. Can you break the number 20 down? Visually do a tree in your head. 20 can divide into what and what? 2, so 2 and 10, and then 10 can go 2 and 5. So I have a pair of 2's and a lonely 5, which is negative 4 plus or minus 2 square root 5 over 2. Just because I can't help myself, since the negative 4 and the 2 are both divisible by 2, this actually reduces down to negative 2 plus or minus square root of 5. There's 2 of my zeros. The other 0 is the one we found from synthetic division, from our list. That looks like a plus now. So there's a bit of a variety when it comes to solving quadratics, and I've said that before. You have to keep all of these things in mind. If it doesn't factor pretty, we have no more potential rational zeros on my list, you might have to do the quadratic formula. Sound good? Let's bring back a theorem that you learned. I know it's called the fundamental theorem of algebra. The fundamental theorem of algebra says that if f of x is a polynomial of degree n, where n is greater than or equal to 1, then the equation f of x equal to 0 has at least one complex root. But it goes on that if a polynomial is of degree n, then containing multiple roots separately, the equation has n roots. So counting multiplicities, we have that many roots. Maybe not necessarily that many individual or unique x-intercepts, but we have that many repeated and unique x-intercepts. We also know that if a plus bi is a root of the polynomial, then the imaginary number, its conjugate, a minus bi, is also a root. You have to give me complex numbers in pairs. They're called conjugate pairs or complex conjugates. Now, this problem, example 5, gives us a bit of a head start. It says solve by first graphing to find x-intercepts. So somebody who has a calculator already out on their desk, can you please graph what this function looks like and tell us where it crosses for sure the x-axis? Yeah, if we're looking at that picture of the graph, from the graph, where does it for sure cross the x-axis? At 2. So we know at least one of the zeros is at x equal to negative 2. But also, what's exactly happening when it's at 2 on the graph? Is it crossing or is it bouncing? It's bouncing. So its multiplicity is 2. Because it bounces right there. So it's a multiplicity of 2. So it's repeating twice. What we learn from that is that we can do synthetic division twice with the number 2 to take out both of those zeros that we know exist from the graph itself. So what I'm going to do is I'm going to set up a double synthetic division. It's really fun. Are you ready? I'm going to divide it first by 2. So my coefficients are 1, are 0, are negative 6, negative 8, and 24. Whoa, where's that 0 from? Yeah, I'm missing an x cubed term. So it's 4, 3, 2, 1, so I have to put a 0 where the 3 goes. Great. Ooh, that hurt my ears. Your shoe was so strong against the floor. We bring down. We multiply. We add. We multiply. We add. We multiply. We add. We multiply. We add. We smile because our remainder is 0. That's what we wanted. We know that has to happen though because we see that it says 0 of the function. So we knew we should get 0 as a remainder. But I also know that since it bounces at 2, I could divide by 2 again. So I'm just going to extend this synthetic division. I'm going to divide by 2 again. Same vibe though. So you're still going to bring down multiply, add, multiply, add, multiply, add, and smile. Because we got, again, a 0. Easy peasy lemon squeezy, yes? So after we divide away the things we notice from the graph, maybe that's 2 different x-intercepts, like if we see it crosses at 5 and at 2, you would divide by 5, then you divide by 2. We see a bounce at 2, so we divide by 2 twice. We're going to take the leftover quotient and both of our divisors, and we're going to write our polynomial the way we have it right now. It is currently factored to be x minus 2 squared, multiplicity 2. And then we have x squared plus 4x plus 6, hopefully equal to 0. Did I lose anybody on the blues and the green? I mean purple.
So whatever the x is, that's the multiplicity as well.
However many times that you have to divide by it, that would be the multiplicity. So like I divided by 2 twice, so the multiplicity is 2.
Yeah, so.
Wait, ask your question again. I didn't understand it.
Why are you dividing it twice?
That's a great question. If we look at the graph again, this equation, when I graphed it, touches the x-axis at -2 but bounces. And in section 3.1 or 3.2, anytime something bounces off the x-axis, it has a multiplicity that's doubled.
So what if it's something else?
Like, what if it's a cross through at 2 and a cross through at 3? You would have written like x minus 2, x minus 3. Because it's not multiplicity. It's just 2 separate zeros.
So you wouldn't do that, you would just do the division twice?
You would do the division twice by the first number and then by the second number, whatever the zeros are. Ours just happens to be a repeating 0, so use the same one. Okay, but at this point, we have it down to a quadratic in purple. Does this quadratic factor? Sounded dramatic in the hallway. Does it? What multiplies to 6 and adds to 4? Nothing. Which means we have to think about other ways to solve this quadratic, which would be what again? Quadratic formula. X equal to -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. While I'm at it, the blue stuff does solve down to 2. Just like it's too easy, can't help myself. But that's a repeated 2, so multiplicity 2, if that helps. Okay, let's start to reduce this guy. So inside for my discriminant, we have 16 minus 4 times 1 times 6. Well, 4 times 1 times 6 is 24. All over 2. What's 16 minus 24? -8. Hopefully your spidey sensors are going off. What's going to happen in this problem? We're going to have an imaginary number. Can you break down 8 at the same time, Doe? What does 8 break down to if you did a tree? 2 square root of 2. So I'm going to write this as 2i square root of 2, all divided by 2. The I comes from the negative. 8 would break down to 2 times 4, and 4 is 2 times 2. So we have a pair of 2's and a lonely 2. But of course, can't help myself. Look at all those 2's in there. We can totally divide some of those out so that we have our complex conjugates of -2 plus and minus I root 2. And so just to make sure we have the right number, right? We have a degree 4 polynomial. How many zeros should I have for a degree 4 polynomial? Degree 4? 4. Here's 2 of them. And since this has a multiplicity of 2, those are the other 2's. So I do have 4 roots here. I have 4 zeros. I have a repeated root at 2, and then I have 2 imaginary roots. I think problems like this are super fun. Look at that double synthetic division there. You're like, yeah, my squiggly, move on. Okay, last thing here is, you learned it last year, linear factorization theorem. The linear factorization theorem sounds crazy. It's just advanced foiling. And we're good at foiling. We've practiced this already. The linear factorization theorem says that if you have a polynomial, then you could write it in terms of its factors as long as there's some number in front to account for a scalar multiplier. Okay? In words, an nth degree polynomial can be expressed as a product of a non-zero constant, that's this non-zero constant, and n linear factors, where each linear factor has a leading coefficient of 1. So what this allows us to do is take information like we have in example 6 and write a standard form polynomial in the correct format. It says to find a fourth degree polynomial function f of x with real coefficients that has -2, 2, and I as zeros, and such that f of 3 is equal to -150. Oh boy, let's get started. Are you ready? This information of having zeros at -2, at 2, and at I tells me the following information. It tells me that my polynomial can be written as some number that I'm going to figure out later, multiplied by x plus 2, multiplied by x minus 2, multiplied by x minus I, and x plus I. So a question for you. I highlighted 3 things, but I wrote 4 factors. How come? It is a fourth degree, yeah, but how did I know to do that with the I?
Because the I comes from the square root, so it's plus or minus.
Correct. I's always come in pairs, so you need the plus version and the minus version each time we do it. Sound good? Our job now is to just figure out what that a sub n number should be. The information I have to help me figure out a sub n is f of 3 equal to -50. So what I'm going to do is I'm going to take the entire function I just wrote, and I'm going to substitute the number 3 into the function and set it equal to -150. So it would look like this. -150 is equal to some number that I don't know, multiplied by 3 plus 2, multiplied by 3 minus 2, multiplied by 3 minus I, multiplied by 3 plus I. Part of this real easy. What's 3 plus 2? 5. What's 3 minus 2? 1. Okay, it's looking good so far. Do you notice that 3 minus I and 3 plus I are a difference of 2 squares? You could FOIL that if you wanted to, or you remember the shortcut that you square the first thing, square the second thing. That is the difference of 2 squares. The center terms would cancel out if you FOILed it. Are your spidey senses going off? What is -1? I squared is -1, so you could just take it and be like, never mind, not I squared, we're going to put a -1 there, which is 9 minus -1. What is 9 minus -1? What? 10. All right, because it's 9 plus 1. So we have a sub n times 5 times 1 times 10. 50. So we have -150 being equal to 50 a sub n. Can we figure out what a sub n is then? Divide by what on both sides? Divide by 50 on both sides. -150 divided by 50 is what? -3. Ooh, we're entering wild territory. I totally did this problem wrong on my teacher notes that I'm sitting right here, but this is correct on the board. We're going to have to check my work as we go. Okay, amazing. We figured out a sub n. Let's go back and let's plug it into the big thing. Oh dear, here we go. So we have f of x is equal to -3 times x plus 2 times x minus 2 times x minus I times x plus I. If the question asks you for factored form, you're done. It's not going to, though. This is, just for yourself for later, this is factored form. you are going to want to write this equation in standard form. So we're going to FOIL like crazy. I know you're excited about it. But let's make ourselves have an easier time with this. Do you see that these are difference of two squares? Do you see that these are difference of two squares? Let's multiply those first. So if we're starting to multiply this out, that negative 3, we'll just tell it, wait a second. This is going to turn into x squared minus 4. And the green, again, turns into x squared minus I squared. Hopefully your spidey senses are going off again, because I squared, what can I change it to? Negative 1. So I'm just going to go ahead and say, just kidding, negative 1. So then I have x squared minus minus 1, which is really what? Plus 1. So we have negative 3 times x squared minus 4 times x squared plus 1. Now we have to actually FOIL, because there's no more shortcuts. These don't happen to be the difference of two squares, so I can't do that trick again. So we're going to leave that negative 3 in the front for a second. We're going to FOIL. X squared times x squared is x to the 4th. X squared times 1 is x squared. Negative 4 times x squared is negative 4x squared. And negative 4 times 1 is negative 4. The last step is real easy. It's just distribution. Multiply everything by negative 3. This is negative 3x to the 4th minus 3x squared. Oh, wait. Skirt, I lied. What can I do in the center here? I forgot about combining like terms. What am I doing? Let's do that first. I'm sorry. I could have distributed then combined like terms, but now we distribute negative 3x to the 4th plus 9x squared plus 12. Here's our f of x function in standard form using the linear factorization theorem. Whoa. Amazing math. Can we ask a question though? Because I'm assuming we have one. That's all one problem.